Hi guys, welcome to Mr. E Physics. Today we're going to be looking at activity and half-life. So this is part of P4, which is radioactivity. What we're going to do is we're going to look at what background radiation is, calculate activity, define half-life, and use a graph to calculate the half-life of a material. So we've got four different scenarios here. Flight from New York to LA, sleeping next to someone, eating a banana, or having an X-ray at a dentist. Which of these do you think you would get the highest dose of radiation from? Well, sleeping next to someone is the lowest, eating a banana, having an X-ray at the dentist, and a flight from New York. Now, these here are all sources of background radiation. So, for example, things like a banana or sleeping next to someone, everything is radioactive. Everything around us is radioactive. It's just that it's very, very low amounts of radiation that are being emitted, and the activity, i.e. the rate that it's decaying, is incredibly low. Bananas are notorious for being more radioactive than other substances. I think it's selenium they contain. If you have an X-ray, well, an X-ray is an ionizing radiation you make from a high PD electric circuit, very similar to gamma. You get a very high dose of radiation from that, and flights from New York to LA, well, any flight, essentially, you are getting exposed to cosmic rays, i.e. high energy radiation from the sun. So this is what background radiation is. If you have this thing called a Geiger counter, if you turn a Geiger counter on, you will pick up radiation even though there's no radioactive sources nearby. So this is background radiation. It's radiation naturally given out from the sources around us. So typically the things that give out the most amount of background radiation are things like rocks. Now these are things that can affect background radiation. So how many flights you have in a year, if you live nearby any rocky structures, things like nuclear power stations, and fallouts from things like nuclear bombs. So if we go back to what we did a few sessions ago, where we were talking about the randomness of something decaying. So if I've got all these uranium nuclei here, you cannot predict when a single nucleus is going to decay. But what you can do is you can predict when some of them decay, which is where we come on to half-life. So this idea that you can't predict when a nucleus decays, we say that radioactivity is random. Now, when we're looking at when something decays, we look at this thing called activity. Activity is the rate unstable nuclei decay. Rate is a word that AQA love. Rate means how much in a certain amount of time. So if you look at the equation here for activity, it's the number of nuclei decaying divided by the time in seconds. Now the unit is called a becquerel, capital B, little q. You are not given this equation, so you need to remember it. So the activity is the rate that unstable nuclei decay. So here's two questions, press pause, have a go. Right, so the answers. If you've got 6,000 decays in 60 seconds, it's going to be 6,000 divided by 60, cancel each other out, to 100. Next. Scientist takes 120 counts in 1 minute. What is the activity? We like to do this a lot. We have time in different units. 1 minute is 60 seconds. It's always good to do that at the start of a question. Get out of the way, get yourself some marks. So 120 in 60, 120 divided by 6 is 2 becquerels. Here's two more questions. Have a go. And here are your answers. Now, we have here a Geiger counter with a Geiger Miller tube here and a radioactive source. The activity of the source is 100 becquerels, but the Geiger counter only records 80 becquerels. Just why? Well, this is where we get onto this thing called count rate. Count rate is slightly different to activity. Activity is the rate that a source decays, but this Geiger counter here might not necessarily be picking up every bit of radiation that's given out by this radioactive source. So it might also be picking out things like background radiation as well. Things like radiation from the wall, or maybe the desk, people in the room, whatever. So activity is the rate that unstable nuclei decay. Count rate, if you ever hear of it, is just the rate that a Geiger counter would detect some form of radioactivity. Okay, so when we were talking about earlier about the randomness of decay, we cannot predict when one nuclei will decay. But what we can do is we can predict when around half of the nuclei decay. Now that sounds obscene, but think of the number of nuclei you would have in a substance. You're going to have, think about it, if you had 238 grams of uranium, you would have a mole of uranium, 6.02 times 10 to the 23 particles. That is a lot of particles. So the randomness here kind of does break down a bit. So if we look here, what we can do is we can predict roughly when half of these nuclei are going to decay. We don't know which half. I mean, I've just said that half for one. And that time period there, taken for half, on average, half the number of nuclei to decay, that is called a half-life. Now, after another half-life, what's going to happen is half of the undecayed nuclei remaining are going to decay. So that was one half-life for the first lot. The second lot, there's another half. So in one half-life, you had all of these decaying. In the second one, you had all of these decaying. In the third one, we have them. So as you can see, what's happening is every half-life, half the number of undecayed nuclei are decaying. And what's also going on is your activity is halving as well. In the first one, you had 20 nuclei decaying. In the second one, you had 10. The third one, you have 5. So half-life is the average time taken, and average is such an important word, for half the number of undecayed nuclei to decay, or the average time taken for half the number of half of the activity. Another thing to note here is you may notice, right, there's 5 remaining. How's it going to be half? Well, it's not going to be half. It's probably going to be 2, maybe 3. When you have such a large amount of particles, on average, this law will work out. So here you have a graph, and what you have to do is you have to work out the half-life using this graph. So a half-life is the average time taken for the activity or the number of undecayed nuclei to half. So if you think about it, look, we're starting off here at 100. After a half-life, that activity is going to have halved. Well, when you halve 100, you get to 50. So what you do is you get a ruler and you go across to where you meet the graph. You then go down. So I've just seen there that it takes 5,700 years for the activity to halve. Now, after another half-life, it should halve again. So if we go now from 50 to 25, we go across. That from there to there is another 5,700 years. And you could do this again. Half of 25 is 12 and a half, etc., etc. So you can see this gap here is always the same. It's 5,700 years. Now, I have seen exam questions where they'll try and catch people out. People just think, oh yeah, you do it once. You just need to do it for this first one here. 5,700 years. It's the average time taken. They're going to be looking for you to do repeats, like there and there. But what they're also going to be looking for you to do is measure the width of these parts here. Let's come. Measure the widths of that, that, and that. Because it might be on this one, the width is 5,700. On this one, it's 5,600, and this one, it's 5,800. It's the average time taken. So if you look, the time here, it does vary. So what do you do next? Well, what you need to do is take a mean of your results. So you take a mean of 5,700, 5,600, and 5,800, and that will be your half-life. In this case, it would be 5,700 years. So here's another one. Same thing, start at 80, so half that would be 40. You need to use a ruler for this one. I mean, that is just catastrophic what I've just done there. Use a ruler, go across and down. So that is 2 days. After another half-life, another 2 days there, another half-life, another 2 days there. So here are 3 graphs. Have a pause, See if you can work out the answer. So the first one is 5 days. Second one is 6 days. Third one, 5 days again. And the fourth one, now the fourth one here is tricky because it goes to there. That there is 6,000 years. Now if you notice, half-life does vary quite a lot from material to material. Some have a half-life of a few hours, some have a half-life of a couple of thousand years. It depends on the substance. The more unstable it is, the shorter the half-life. Now this half-life property is really useful because sometimes we want things that have quite a short half-life. That's because you don't want it to be radioactive for a very long time. We'll come to that when we look at uses of radioactivity. So what you might have to do as well is maybe not use graphs, but use the half-life to work out either what its activity is going to be after a certain amount of time, or maybe what the half-life of a substance is. So have a look at these two questions. We'll go for the answers in a sec. Right, so radioactive substance has an activity of 160 becquerels, a half-life of 2 hours. What's the activity after 6 hours? Right, so in 2 hours, it's going to have halved. And it will halve from 160 to 80. After another 2 hours, it's going to have halved again. So now we're on 4 hours. So it's going to go from 80 to 40. After another 2 hours, we're getting to 6 hours, which is what we want. It halves again, and now we're going from 40 to 20. So the activity should be after 6 hours, 20 becquerels. Right, the activity of a sample decreases to a 16th of its original value over 24 hours. Calculate its half-life. Right, so what we can say is, let's say we're at time 0, and we have 100% or 1 of our isotope. After a half-life, it's going to have gone down to half. So there's your first half-life. After a second half-life, that half is going to have halved again. That's a quarter. After a third half-life, it's going to have to reduce to an eighth. And after a fourth, I'm running out of room, it's going to reduce to a factor of 16. So if you look, it's gone through 4 half-lives. So this substance has halved in number of undecayed nuclei by 4. So it's taken 24 hours to do that. So if we do 24 divided by 4, 6. If we have 6 hours for the first one, and therefore 12 for the second one, 18, 24, the half-life is 6 hours, because after every 6 hours here, the activity is halving to get to 1 over 16. You could even say that after a half-life, or after a certain number of half-lives, you have 1 over 2 to the n being the number of half-lives. So if you've gone through 3 half-lives, you will have 1 over 2 to the 3, you will have 1/8 of your substance remaining. Hope that's been helpful. See you next time.